Hello and welcome to NEET course. We will be studying chemistry in everyday life. Drugs and their classification. Drugs are chemicals of low molecular mass, that is 100 to 500 U. They interact with macromolecular targets and produce a biological response. If this biological response is useful and therapeutic, then these chemicals are called as medicines, and they are used in diagnosis, prevention and treatment of diseases. Most of the drugs which are used as medicines are potentially poisonous if we take them in higher doses than those which are recommended to us. Use of chemicals for therapeutic effect is called as chemotherapy. Use of chemicals for therapeutic effect is called as chemotherapy. On the basis of pharmacological effect, that is drugs are classified on the basis of pharmacological effect, drug action and chemical structure. This classification of pharmacological effect is useful for doctors because it provides them whole range of drugs available for treatment of a particular type of problems. For example, analgesics, they have pain-killing effect. Antiseptics kill or arrest the growth of microorganisms. Then on the basis of drug action, it is based on the action of a drug on a particular biochemical process. Action of a drug on a particular biochemical process. For example, antihistamines inhibit the action of the compound histamine, which causes inflammation in the body. Antihistamines inhibit the action of the compound histamine, which causes inflammation in our body. So in our body, histamine causes inflammation, that is allergic response or allergic reaction, and antihistamines, they stop this or inhibit the action of the compound histamine. There are various ways in which action of histamine can be blocked. Then on the basis of chemical structure, it is based on the chemical structure of the drug. Drugs classified in this way share a common structural feature and often have similar pharmacological activity. For example, sulfonamides, this is the structure NH2 attached to benzene ring, and SONHR. This is the structure of sulfonamide. On the basis of molecular targets, and lastly on the basis of molecular targets, drugs are usually interact with biomolecules such as carbohydrates, lipids and proteins and nucleic acid. These are called as target molecules. So drugs usually interact with biomolecules such as carbohydrates, lipids, proteins and nucleic acids. So these are called the target molecules or the drug targets. Drug possessing some common structural features may have the same mechanism of action on targets. The classification based on molecular targets is most useful classification for medicinal chemists. So there will be a group of drugs which will be targeting proteins or carbohydrates or lipids or nucleic acids. So these are the target molecules or drug targets. That is these carbohydrate, lipid, molecule and nucleic acid. So drugs possessing some common structural features may have the same mechanism of action on targets. The classification based on molecular targets is the most useful classification. Which is the most useful classification of the four classifications? That is, the first one was on the basis of pharmacological effect, that is used by doctors to solve a problem. Then drug action, that is how drug inhibits the action of a biochemical process. That is action of on a particular biochemical process. Third was on the basis of chemical structure, that is structural similarities of a lot of drugs, that is they give the same pharmacological activity. And lastly was on the basis of molecular targets. Molecular targets are drug targets such as carbohydrate, lipid, nucleic acid and protein. That is, there will be some drugs containing the same feature which will have the same mechanism of action on these targets. And this classification on the basis of molecular targets is the most useful classification for medicinal chemists. Then macromolecules of biological origin perform various functions in the body. So macromolecules of biological origin perform various functions in the body. For example, proteins, which perform the role of biological catalyst in the body, are called as enzymes. So we know that enzymes are essentially proteins. So the proteins which perform the role of biological catalyst in the body, they are called as enzymes, and those which are crucial to communication system are called as receptors. And those enzymes which are crucial to communication system in our body are called as receptors. So proteins which perform function of role of biological catalyst in the body are called as enzymes, and those proteins which are crucial to communication system in the body are called as receptors. Carrier proteins carry small polar molecules across the cell membrane. Nucleic acids have coded genetic information for the cell. Lipids and carbohydrates are structural parts of the cell membrane. So nucleic acid have coded genetic information for the cell, and lipids and carbohydrates are the structural part of the cell membrane. So proteins act as catalysts, that is biocatalysts, that is enzyme for the body. Then they are those proteins which are crucial for the communication system in our body. They are called as receptors. Carrier proteins, they help transport the hydrophilic substances or polar substances, that is those which are not soluble in non-polar solvents like benzene and all. Then they help to carry them across the cell membrane, transportation by carrier proteins. Then nucleic acids have coded genetic information for the cell, that is in our nucleus, for the inheritance of progeny. Then lipids and carbohydrates are the structural part of the cell membrane. So now enzymes as drug target. So this was macromolecules, drug target interaction, macromolecules in having functions in our body. Now enzymes as drug targets, catalytic action of enzymes. For understanding interaction between a drug and an enzyme, it is important to know that how enzymes catalyze the reaction. In the catalytic activity, enzymes perform two major functions. What is the first function? The first function is of an enzyme is to hold the substrate for a chemical reaction. So the first function of an enzyme is to hold the substrate for a chemical reaction. So the first function of an enzyme is to hold the substrate for a chemical reaction. Active sites of enzymes hold the substrate molecule in a suitable position so that it can be attacked by the reagent efficiently. So if this is an enzyme, then the first function of the enzyme is to hold the substrate for a chemical reaction. So this is the, let's say, the substrate. So this will be the active site of the enzyme, and in this the substrate will be held in a suitable position so that it can be attacked by the reagent effectively. So substrates bind to the active site of the enzyme through variety of interactions such as ionic bonding, hydrogen bonding, van der Waals interaction, and dipole-dipole interaction. So how does the substrate and the enzyme, that is how is the enzyme uh, holds on to the substrate. How does the enzyme hold on to the substrate? That is, and how does the substrate bind to the active site of the enzyme? It binds by a variety of interactions, such as it can be either ionic bonding, or it can be van der Waals interaction, or it can be dipole-dipole interaction, or it can be hydrogen bonding. So ionic bonding, hydrogen bonding, van der Waals interaction, dipole-dipole interaction. What is the second function of an enzyme? It is to provide functional groups which will attack the substrate and carry out a chemical reaction. So first is to hold the substrate in its place with the help of an active site which is present on the enzyme, and ionic bonding or hydrogen bonding or van der Waals interaction or dipole-dipole interaction. Then the second function of an enzyme is to provide functional groups which will attack the substrate and carry out the chemical reaction. So now that the substrate has binded to the active site of the enzyme, now the reaction has to be proceeded. How does it proceed? That is, the the enzyme has functional groups, and these functional groups will attack the substrate, and then the chemical reaction will be carried out. Second comes the drug enzyme interaction. Drugs inhibit any of the above mentioned activities of enzymes. These can block the binding site of the enzyme and prevent the binding of substrate. So what happens when drugs come into place? That is, drugs inhibit any of the above mentioned activities of enzymes. So that is the attachment of substrate to the active site of the enzyme, as well as carrying out of the reaction, that is, all of these, they can be inhibited by drugs. And how? That is, the drugs can block the binding site of the enzyme and prevent the binding of substrate, or they can inhibit the catalytic activity of the enzyme, and such drugs are called as enzyme inhibitors. So all the activities of an enzyme can be inhibited or stopped with the help of drugs. How do the drugs work? These drugs block the binding site of the enzyme, that is, the binding site of the enzyme, that is the active site. It can be blocked by the drugs, uh, or they can change the active site altogether to prevent the binding of the substrate, or they can inhibit the catalytic activity. That is, even after binding, the catalytic activity of the chemical reaction will not proceed. The catalytic activity of the enzyme will only stop. So such drugs are called as enzyme inhibitors. That is, they inhibit the action of the biocatalyst, that is the enzyme. Drugs inhibit the attachment of substrate on active site of enzymes in two different ways. Firstly, drugs compete with the natural substrate for their attachment on the active sites of enzyme, and such drugs are called as competitive inhibitors. So how do the drugs inhibit the attachment of substrate on active site? There are two ways. Firstly, competitive inhibition and non-competitive inhibition. So in competitive inhibition, the drug, which is an inhibitor, it competes with the substrate to bind to the active site. So drug which is an inhibitor, it competes with the substrate to bind to the active site. So here the drug is there, here the substrate is there, and here is the active site of the enzyme, and both compete with each other. So they are actively competing for the active site of the enzyme. So just in case, that is, the drug is present in more concentration, and or it has more affinity to bind with the active site of the enzyme, and the drug binds with the enzyme instead of the substrate, then the reaction will not proceed. So that is, drug has blocked the active site of the enzyme. So such drugs are called as competitive inhibitors. Now some drugs do not bind to the enzyme site. Some drugs are like, itna jhagda kaun karega? So these they bind to a different site of the enzyme, and this is called as allosteric site. So if this is if this is our enzyme, then here is the active site. So in competitive inhibition, the substrate and the drug, both of them were competitively trying to attach themselves with the active site. But नॉन कॉम्पिटिटिव इनहिबिशन में जो जो ड्रग इनहिबिटर आया उसने बोला कि इतना मेहनत करके compete क्यों करूँ मैं substrate के साथ. So there is an allosteric site is there. This is the allosteric site, which is a different site other than the active site on an enzyme. So they do not bind. So this inhibitor that came, he said that I will not compete and bind with the active site. I will rather go and bind with the allosteric site. So in this allosteric site, which is another site on the enzyme other than the active site, the moment this inhibitor will bind, then it will change the shape of the active site altogether such a way that the substrate cannot recognize it. Substrate क्या कोई भी आके फिर bind नहीं कर पाएगा. So उसका it will change after binding with the allosteric site. Here it has binded with the allosteric site. The enzyme inhibitor, it changed the shape only. So it changed the shape of the active site. So now no substrate can recognize it. If the bond formed between the enzyme and an inhibitor is a strong covalent bond and cannot be broken, so if now in this case, if the So if the bond formed between an enzyme and an inhibitor is a strong covalent bond and this bond cannot be broken easily, then the enzyme is blocked permanently and the body then degrades the enzyme inhibitor complex and synthesizes the new enzyme. So in this case, if at the allosteric site the inhibitor which has attached itself to the enzyme, if it has attached itself by strong covalent bonds, then nothing else can be done. That is, the strong covalent bond cannot be broken easily, and therefore the enzyme will be blocked permanently. That is, in such a case, the body then degrades the enzyme inhibitor complex and synthesizes new enzyme. In such case, there is in that like nothing can happen and no substrate can combine to this to the enzyme. Then this enzyme inhibitor complex is then degraded and a new enzyme is synthesized. Now receptors as drug targets. Receptors are proteins that are crucial to body's communication process. Majority of these are embedded in cell membranes. So now receptors as drug targets. First we saw enzymes. First we saw enzymes as the drug targets, how the drugs target the enzymes. Now we will see how the drugs target the receptors. So receptors, what are receptors? Enzymes were proteins which were biocatalysts in our body. Receptors are proteins which are crucial in the body's communication process, and majority of these, they are embedded in the cell membrane. So receptor proteins are embedded in the cell membrane in such a way that their small part possessing active site projects out of the surface of the membrane and opens on the outside region of the cell membrane. So how is receptor embedded in the cell membrane? It is embedded in the cell membrane in such a way that uh, the small part possessing the active site projects out of the surface of the membrane and opens on the outside region of the cell membrane. So here we took a small part of the cell membrane or plasma membrane of an animal cell. This is an animal cell, and on enlargement we saw that this is a receptor protein and it is embedded inside the integral protein. It is embedded inside the cell membrane, integral inside. Then here is the inner surface of the cell membrane, here is the outer surface of the cell membrane. So this is the inside and this is the outside. Now in such a way the protein has been embedded. So the protein that is okay, so the protein receptor protein, it is embedded in the lipid bilayer in such a way that the binding site of the receptor protein, it projects out of the projects out of the surface of the membrane, that is and opens on the outside region of the membrane. So this is the outside region of the cell membrane, this is the inside or interior region of the cell membrane. The receptor protein is embedded completely, that is an integral protein inside the lipid bilayer, and this is the binding site of the receptor, which is projecting or protruding out of the cell membrane, and in the outside, that is the small binding site is present on the outer surface of the cell membrane. That is the active site. So in the body, message between two neurons and that between neurons to muscles is communicated through certain chemicals. What are these chemicals? They are neurotransmitters, basically chemical messengers, and they are received at the binding sites of receptor proteins. So the message between two neurons and between neuron and muscle, neuromuscular junction, it is communicated through chemical messengers acetylcholine. If you would remember, neuromuscular junction, acetylcholine. So these chemicals are known as chemical messengers, and they are received at the binding site of the receptor proteins. So to accommodate a messenger, a shape of the receptor site changes. This brings out the transfer of message into the cell. Thus, chemical messenger gives message to the cell without entering the cell. These chemical messengers, which are help in communication between two neurons or a neuron and a muscle, they are known as chemical messengers, and they are received at the binding site of the receptor proteins. So to accommodate a messenger, the shape of the receptor site changes. It depends what kind of shape the chemical messenger is. The shape also changes. That is the shape of the receptor protein. It changes, and then this brings about the transfer of message into the cell. Thus, chemical messenger gives a message to the cell without entering the cell. So this chemical messenger is not entering into the cell; it just binds, and then the message is transferred. So this is the outside containing the binding site. This is the inside or interior of the cell, and this is the chemical messenger. This chemical messenger comes, and according to this chemical messenger, the binding site of the receptor protein changes its shape. Then it binds to it. This is the lipid bilayer of the cell membrane. After it binds to it, it does not enter the cell, that is without entering the cell, it just binds to it, and then the message, that is the transfer of message, takes place. That is over here the message is sent into the cell, and then again then the chemical messenger, it detaches and it goes away after the message has been received. So here see, receptor is receiving the chemical messenger in the first A, then second, the shape of the receptor is changed after attachment of messenger, then receptor regains the structure after removal of messenger. So it depends, it's not necessary that, so in your enzyme, the shape of the active site and that of the enzyme, of the substrate, it mattered, but over here the receptor protein will change its active site or binding site accordingly, and then later it will come back to its shape, it will regain its shape as the chemical messenger is detached. There are a large number of different receptors in the body that interact with different chemical messengers. So we have a lot, that is a huge number of receptors or different receptors in our body which interact with different chemical messengers, and these receptors show selectivity for one chemical messenger over the other because their binding site has shape, structure and amino acid composition. So there are a large number of different receptors in the body, and these different receptors, they interact with different chemical messengers. So we have a large number of different receptors in our body, and they interact with different chemical messengers. These receptors show selectivity for one chemical messenger. So uh, since there are so many different receptors, they are going to show selectivity. They are going to be specificity, that is specific. They are going to be specific for one chemical messenger over the other. Why? Because their binding sites have different shape, structure, and amino acid composition. Then drugs that bind to the receptor site and inhibit its natural function are called as antagonists, and they are useful when blocking of message is required. There are other types of drugs that mimic the natural messenger by switching on the receptor. These are called as agonists. They are useful when there is a lack of natural chemical messenger. So antagonist is always, remember, opposite, something opposing. So drugs which bind to the receptor site and inhibit the natural function. So there is some natural function is going on, and these drugs, they bind to the receptor protein, and they send a message or a signal into the cell to inhibit the natural function, that is, they are opposing it. So therefore antagonist, and they are useful for blocking of messages, such as your histamine, antihistamine, you can take an example. But there are drugs which, let's say, production of something is going on in the cell, that is antibody, something like that, and you need it, or an enzyme is being formed, but it is not being formed in enough amount, you need more. So you want to speed up, or you need it fast, you want to speed up the process. So then there are drugs which mimic the natural messengers by switching on the receptor, and these are called as agonists, and they are useful when there is a lack of chemical messenger. So agonist, they show, or synergistic effect. Antagonistic effect is a synergistic effect, that is similar, same thing. They are going to just enhance the natural messenger. Sorry, the natural reaction, the function which is going on. अभी नहीं बोल रहा है, बोल रहा है बाद में कल परसों बोल रहे हैं. Now therapeutic action of different classes of drugs. Firstly, antacids. We know when there is a lot of production of, we know the pH in our stomach is 1.8. Why? Due to hydrochloric acid, highly acidic. So sometimes if we don't eat food for a very long time, then this hydrochloric acid is produced in abnormal amounts, that is more amount than it should be produced. So overproduction of acid in the stomach causes irritation and pain. In severe cases, ulcers are developed. So what's happened to my drawing? So we know that we have mucus layer, and here is HCl. Overproduction of HCl, that is, this mucus lining will slowly it will that is become thinner and thinner and thinner, and the moment the HCl directly touches the lining of our stomach, then it will cause ulcer. This is called as stomach ulcer. So only treatment for acidity was administration of antacids such as sodium hydrogen carbonate or a mixture of aluminium and magnesium hydroxide. So why? Because these are all basic substances. These are all basic substances. So they will reduce the activity of anti-acid. So however, excessive hydrogen carbonate can make the stomach alkaline and trigger the production of even more acid. So if we eat excessive hydrogen carbonate, then the pH will drop suddenly, then our stomach will become alkaline, and this will trigger your oxyntic or parietal cells to secrete even more hydrochloric acid. So metal hydroxides are better alternatives because being insoluble, these do not increase the pH above neutrality. Hydrogen carbonate is soluble, but metal hydroxides such as AlOH whole thrice or MgOH whole thrice, both of these, they are insoluble, and therefore they will not increase the pH above neutrality. These treatments control only symptoms and not the cause. Therefore, with these metal salts, patients cannot be treated easily. In advanced stage, ulcers become life-threatening, and its only treatment is to remove the affected part of stomach. So in extreme cases, due to a lot of production of acid, the stomach ulcers, they become life-threatening, and only treatment for stomach ulcers becomes the removal of the part of stomach which has been affected. So a major breakthrough in the treatment of hyperacidity came through the discovery according to which a chemical, histamine, stimulates the secretion of pepsin and hydrochloric acid in the stomach. The drug cimetidine or Tegamet was designed to prevent the interaction of histamine with the receptors present in the stomach wall. This resulted in release of lesser amount of acid. The importance of the drug was so much that it demanded the largest selling drug in the world until another drug, ranitidine or Zantac, was discovered. So what was the breakthrough in the treatment of hyperacidity? That is, it was discovered that according to that is a chemical histamine, it stimulates the secretion of pepsin and hydrochloric acid in the stomach. It stimulates the secretion of pepsin and hydrochloric acid in the stomach. Pepsin is a protein digesting enzyme, and HCl, hydrochloric acid, in the stomach. And the drug cimetidine or Tegamet, it was designed to prevent the interaction of histamine with the receptors present in the stomach wall. So, due to histamine, the pepsin and HCl both were released in even more amount, that is surplus amounts. So therefore, a drug that is cimetidine or Tegamet was designed, which prevented the interaction of histamine with the receptor of the with the receptors which are present in the stomach wall, and therefore this resulted in release of lesser amount of acid, and the importance of the drug cimetidine or Tegamet was so much that it became the world's largest selling drug until another drug, ranitidine, which you must have heard, or Zantac, was discovered. These are the structures. Now antihistamines. So histamine is a potent vasodilator. So histamine mainly has two functions. Firstly, it causes inflammation, and secondly, it is a vasodilator. How it and it is released by whom? Basophil. So basically, basophil release histamine, serotonin, and heparin. Out of that, for histamine leads to allergic reaction, inflammation due to, that is, allergic reaction. You can say allergic reaction, and it is also a vasodilator. So it contracts the smooth muscles in the bronchi and gut and relaxes other muscles. So it contracts the smooth muscles, that is involuntary muscles, which are present in our bronchi and as well as in our gut, but it relaxes all other muscles such as those in the walls of blood vessel. Therefore it is called as vasodilator, because it dilates blood vessels. Dilates blood vessels. Whereas your serotonin is a vasoconstrictor because it constricts blood vessels. Histamine is also responsible for nasal congestion associated with common cold and allergic response to pollen. So all allergic responses, they are due to histamine, as well as nasal congestion which is associated with common cold, that is also due to histamine. So synthetic drugs such as brompheniramine or Dimetap, and terfenadine or Seldane. They are antihistamines. They are synthetic antihistamines. They interfere with the natural action of histamine by competing with histamine for binding the sites of receptors where histamine exerts its effect. So they show competitive inhibition with histamine. Now the question arises, why do the above antihistamine not affect the secretion of acid in the stomach? The reason is that anti-allergic and antacid drugs work on different receptors. So the receptor which is responsible for antacid is different, whereas for anti-allergen is completely different. So if you are allergic to peanuts, then the moment you eat a peanut, then your histamine in your body, it creates an inflammation and sets out a wide range of reactions. That is, then the moment you are given antihistamine, that antihistamine, it actively undergoes competitive inhibition with your histamine, and antihistamines such as Seldane and Dimetap, that is brompheniramine and terfenadine, they undergo competitive inhibition with histamine, and they bind with the receptor and therefore stop or inhibit the inflammation in our body or allergic response which is happening in our body. For antacids, they are different. Neurologically active drugs. Tranquilizers and analgesics. Tranquilizers and analgesics, they are neurologically active drugs. They affect the message transfer mechanism from nerve to receptor. So tranquilizers and analgesics, both of them are neurologically active drugs and they affect the message transfer mechanism from nerve to receptor. Tranquilizers are a class of chemical compounds used for the treatment of stress and mild or severe mental diseases. They relieve anxiety, stress, irritability, or excitement by inducing a sense of well-being. So both tranquilizers and analgesics, they both are neurologically active drugs. That is, they affect our brain neurotransmitters, and that is neurons, basically our nervous system. They affect the message transfer mechanism. From where do they work exactly? They affect the message transfer mechanism from nerve to receptor. Now, tranquilizers are a class of chemical compounds which are used for treatment of stress, anxiety, mental disorders, irritability, or excitement by inducing a sense of well-being. They form essential component of sleeping pills. There are various types of tranquilizers. They function by different mechanisms. For example, noradrenaline or norepinephrine is one of the neurotransmitters that plays a role in mood changes. Noradrenaline or norepinephrine. So our adrenal gland releases two drugs, that is adrenaline, noradrenaline. Adrenaline is also called as epinephrine. Noradrenaline is also called as norepinephrine. If the level of noradrenaline is low for some reason, then the signal sending activity becomes low. So basically, in people whom noradrenaline is low for some reason, it can be genetic or due to chronic stress or whatever, then the signal sending activity becomes low and the person suffers from depression because it can't send signals so well. In such situations, antidepressants are required. So, so these drugs inhibit the enzymes which catalyze. What do these drugs do? They inhibit the enzymes which catalyze the degradation of noradrenaline. If the enzyme is inhibited, this important neurotransmitter is slowly metabolized and can activate its receptor for longer periods of time, thus counteracting the effect of depression. Iprenosid Iprenozoid, Iprenoziade, Ipreniazid, Iproniazid and Phenelzin, also called as Nardel. So these both are the examples of tranquilizers or antidepressant drugs. They are antidepressants. So let's go back. So noradrenaline is one of the neurotransmitters which plays in a very important role in our mood changes. And if the noradrenaline is low in people for some reason, such as let's say chronic stress or genetic reason, then the signal sending activity becomes very less. And if the signal is not sent, then the person will suffer from depression. And in such situations, antidepressants are required. What do antidepressants do? They basically inhibit the enzyme which catalyzes or works on degradation of noradrenaline. So once that enzyme is inhibited, then the noradrenaline, which earlier was getting inhibited by the enzyme, now can work for longer time, and it is slowly metabolized and it can activate its receptor for longer periods of time, and it counteracts the effect of depression. Example is iproniazid and phenelzine. Some tranquilizers, namely chlordiazepam, chlor chlordiazepoxide and meprobamate, are relatively mild tranquilizers and they are used for relieving tension. Equanil is used for controlling depression and hypertension. So chlordiazepoxide and meprobamate are relatively mild tranquilizers and they are suitable for relieving tension. Equanil is suitable for relieving depression as well as controlling depression and hypertension. Chlordiazepoxide, meprobamate and equanil. Then derivatives of barbituric acid. Example is veronal, amytal, nembutal, all luminal, and seconal. They all constitute an important class of tranquilizers and they are all called as derivatives of barbiturates. Barbiturates are hypnotic, that is sleep producing agents. Some other substances used as tranquilizers are Valium and serotonin. Barbiturates are hypnotic, that is, they are sleep producing agents. Some other substances used as tranquilizers are Valium and serotonin. Veronal, these are all. So veronal, seconal, nicumbutal or nembutal, luminal, vicronal, amytal, these are all barbiturates and they are hypnotic or sleep producing agents. Now analgesics. Analgesics reduce or abolish pain without causing impairment of consciousness. What are analgesics? Analgesics basically reduce pain or abolish pain and they do not cause any kind of impairment of consciousness or mental confusion or incoordination or paralysis or any other disturbances of nervous system. So therefore, like, they do not have any side effects. Analgesics, they only reduce the pain. They are classified as below, that is firstly non-narcotic, that is non-addictive analgesics, and secondly narcotic drugs or narcotic analgesics. So firstly, non-narcotic analgesics are non-addictive analgesics. They are aspirin and paracetamol. So aspirin and paracetamol belong to the class of non-narcotic analgesics. Aspirin is the most familiar example. What does aspirin do? It inhibits the synthesis of chemicals known as prostaglandin, which stimulates inflammation in the tissue and causes pain. So all our muscular cramps as well as menstrual pain, these all are due to prostaglandins, secretion of prostaglandins in our muscles, which stimulates inflammation in the tissue and it causes pain. So these drugs are effective in relieving skeletal pain such as that due to arthritis. So firstly, they inhibit the synthesis of prostaglandin and reduce pain, and secondly, they also reduce or relieve skeletal pain due to arthritis. These drugs have many other effects as well, such as reducing fever, antipyretic, example paracetamol, and preventing platelet coagulation. Because of this anti-blood clotting action, aspirin finds its use to prevent heart attacks. So later on it was found out that that is, they do not let the blood clot. So they kind of act as an anticoagulant. So this is helpful in prevention of heart attacks. Prevention of blockage of arteries and blood vessels, which prevents eventually heart attack. Then narcotic analgesics. Narcotic analgesics are morphine and many of its homologues. When administered in medicinal doses, they relieve pain and produce sleep. In poisonous doses, they produce stupor, coma, convulsions, and ultimately death. Stupor, that is still that is जैसे हाथ पैर ऐसे टेढ़े ये होके ये stupor you say in a particular ये paralysis kind of coma, convulsions and ultimately death. Morphine narcotics are sometimes referred to as opiates. Why? Because they are obtained from the opium poppy plant. Then these analgesics are chiefly used for the relief of post-operative pain, that is after operation, then cardiac pain, pain of terminal cancer and childbirth. Morphine, heroin and codeine. So these are non-narcotic narcotic analgesics are morphine, heroin, codeine. They relieve pain and produce sleep when taken normally, but in higher doses they produce stupor, coma, convulsions and death. Then antimicrobial. Diseases in human beings and animals may be caused by a variety of microorganisms such as bacteria, virus, fungi and other pathogens. And antimicrobial, what does it do? It tends to destroy or prevent development or inhibit the pathogenic action of microbes such as bacteria, that is antibacterial drugs, fungi, antifungal drugs, virus, antiviral drugs or other parasitic, antiparasitic drugs selectively. That is what an antimicrobial basically does. So antibiotics, antiseptics and disinfectants, they are all antimicrobial drugs. Antibiotics. Antibiotics are drugs which are used to treat infection because of their low toxicity for humans and animals. They are highly toxic to whom? Bacteria. Antibiotics, right? So antibiotics are used to treat infections because of their low toxicity for humans and animals. Initially, antibiotics were classified as chemical substances produced by microorganisms, bacteria, fungi and mold that inhibit the growth or destroy microorganism, but the development of synthetic methods has helped us in synthesizing some of the compounds which are originally discovered as products of microorganisms. Some purely synthetic compounds have antibacterial activity and therefore definition of antibiotic has been modified. Earlier antibiotic was something which we got as a product of microorganism. Earlier antibiotic were discovered as product of microorganism, but now we can make synthetic antibiotics too. Therefore the definition of antibiotics has been modified. An antibiotic, what does an antibiotic now refer as? Antibiotic now refers as a substance produced wholly or partly by chemical synthesis in which low concentrations inhibits the growth or destroys microorganism by intervening in their metabolic processes. So basically, that is antibacterial medicines, they would stop the cell wall from growing in a bacteria, that is something in their metabolic pathway, that is from their DNA replicate, that is stop antiviral, they will stop the DNA replication, something like that, RNA. And also, that's that. Then the search for chemicals that would adversely affect invading bacteria but not the host began in 19th century. So firstly, Paul Ehrlich was a German bacteriologist. He conceived this idea and he investigated arsenic-based structure in order to produce less toxic substances for the treatment of syphilis. So syphilis is caused by a bacterium called as Treponema palladium, which causes syphilis, and it is a bacterial infection. So for that we need to have antibiotics. But Paul Ehrlich, who was a German bacteriologist, he conceived this idea that we need to search for chemicals which would kill the microorganism, but they would not affect us humans and animals adversely. So he investigated arsenic-based structures in order to produce less toxic substances for treatment of syphilis. He developed the medicine arsphenamine and known as sulverson. So he developed the medicine arsphenamine containing arsenic, which is known as sulverson, and he got Nobel Prize for medicine in 1908 for this discovery. It was the first effective treatment discovered for syphilis. First effective treatment was discovered for syphilis. Although sulverson is toxic to human beings, its effect on the bacteria, spirochete, also known as spirochete, which causes syphilis, is much greater than its effect on human beings. At the same time, Ehrlich was working on azodize also, and he noted that there is a similarity in the structure of sulverson and azodie. How? That is the arsenic linkage present in arsphenamine resembles the nitrogen-nitrogen linkage present in azodie in the sense that the arsenic atom is present in place of nitrogen. He also noted that tissues getting colored by dyes selectively. Therefore, Ehrlich began to search for the compounds which resemble in structure to azodize and selectively bind to bacteria. In 1932, he succeeded in preparing the first effective antibacterial agent, that is Prontosil. So which resemble in structure to the compound sulverson. Soon it was discovered that in the body Prontosil is converted to a compound called sulfenilamide. Prontosil got converted into a compound called sulfenilamide, sulfanilamide, which is the real active compound. Thus, sulfa drugs were discovered. A large range of sulfonamide analogues that is similar in function, they were synthesized, and one of the best effective is sulfapyridine. Despite the success of sulfonamides, the real revolution of antibacterial therapy began when Alexander Fleming in 1929 discovered the antibiotic properties of Penicillium fungus. You must all know the story. That is, he took a petri dish and in that he was growing the culture of Streptococcus pneumoniae, but he forgot to wash it properly and he saw that a mold was growing, that was Penicillium, and the Streptococcus pneumoniae grew around it, but could not grow through it or with it. That is, it was in some way it was inhibiting the growth of uh, bacteria. So isolation and purification of active compound to accumulate sufficient material for clinical trials took 13 years. Antibiotics have either cidal killing effect or static inhibitory. So bactericidal and bacteriostatic. Bactericidal, that is cidal. Clinic, they will kill directly, they will kill, or they will inhibit. So penicillin, aminoglycosides, and oflozaxin, all three of them have cidal or killing effect. That is, if you eat these antibiotics as per your prescription and finish the course, then they will kill the bacteria. bacteriostatic, they will inhibit the effect of microbes. They won't kill, they will inhibit. Erythromycin, tetracycline, and chloramphenicol. The range of bacteria or other microorganisms which are affected by certain antibiotic is expressed as its spectrum of action. Antibiotics which kill or inhibit a wide range of gram-positive and gram-negative bacteria are said to be broad-spectrum antibiotics. What are broad-spectrum antibiotics? When you have an infection and we are not able to find out, and we know it is a bacterial infection, but what kind we are not able to find out exactly, then we give you broad-spectrum antibiotics. Broad-spectrum antibiotics, that is, at a large, they will work on the most common, that is an antibiotic which can inhibit the growth of bacteria in 5 or 6 diseases. It is termed as broad spectrum antibiotic. Those effective mainly against gram positive or gram negative bacteria are narrow spectrum antibiotics. It's effective against a single organism or disease, and they are referred to as limited spectrum antibiotics. So narrow spectrum antibiotics are also called as limited spectrum antibiotics. Why? Because they are efficient against only a particular disease, pathogen, single organism. Ampicillin and amoxicillin are synthetic modifications of penicillin. Penicillin G has narrow spectrum. These Penicillin G has a narrow spectrum, whereas ampicillin and amoxicillin, they are broad spectrum. It is absolutely essential to test the patient for sensitivity or allergy to penicillin before it is administered. In India, penicillin is manufactured in Hindustan Antibiotics in Pimpri. Hindustan Antibiotics in Pimpri, which is a in private sector industry. Now, chloramphenicol was isolated in 1947. It is a broad spectrum antibiotic. It is rapidly absorbed from the gastrointestinal tract, and it can be given orally in the case of typhoid, dysentery, acute fever, certain form of urinary infections, meningitis, and pneumonia. So chloramphenicol, chloramphenicol, chloramphenicol. Chloramphenicol was isolated in 1947. It is a broad spectrum antibiotic. It is rapidly absorbed from the gastrointestinal tract, and it can be given orally in the case of typhoid, dysentery, acute fever, certain form of urinary infection, meningitis, and pneumonia. Vancomycin. Vancomycin and ofloxacin are other important broad spectrum antibiotics. The antibiotic digi, digidazirin is supposed to be toxic towards certain strains of cancer cells. General structure of penicillin. And chloramphenicol. Antiseptics and disinfectants. Antiseptics and disinfectants are also the chemicals which either kill or prevent the growth of microorganisms. Antiseptics or disinfectants are also the chemicals which kill or prevent the growth of microorganisms. Antiseptics are applied to living tissues such as wound, cut, ulcer, and diseased skin surfaces. They are not really ingested per se. Antiseptics are applied to living tissues such as wounds, cuts, diseases, diseased skin surface, ulcers. Examples are furacin and soframycin. Furacin and soframycin, they are not ingested like antibiotics. They are commonly used as antiseptic. Dettol is a mixture of chlorazinol and terpinol. Dettol is a mixture of chlorazinol and terpinol. Bithionol is the bithionol. The compound is also called as bithionol. Is added to soaps to impart antiseptic properties. Bithionol. is added to soaps to impart antiseptic properties. Obviously, because you use soaps, right? You apply it in your skin. So iodine is a powerful antiseptic. It has that is its 2 to 3% solution in alcohol and water. Alcohol water mixture is called as tincture of iodine. It is applied on wounds. Iodoform is also used as an antiseptic for wounds. Boric acid in dilute aqueous solution is used as a weak antiseptic for dyes. Boric acid in dilute aqueous solution is used as a weak antiseptic for eyes. Disinfectants. Disinfectants are applied on inanimate objects such as floors, drainage system, instruments, etc. Some substances can act as antiseptic as well as disinfectant by varying the concentration. For example, 0.2% solution of phenol is an antiseptic while 1% solution is a disinfectant. What are disinfectants? They can be applied to inanimate objects such as floor, drainage system, instrument, etc. Some substances are there which can act as disinfectants as well as antiseptics by varying the concentration. For example, 0.2% of solution of phenol is an antiseptic while 1% of solution is a disinfectant. Why? Because antiseptics we apply it on our skin, right? Even if at external use, still we apply it on our skin. So we can't use higher concentration. But on inanimate object doesn't matter how much, even if it is higher concentration, we can put. So chlorine is the chlorine in the concentration of 0.2 to 0.4 ppm in aqueous solution and sulfur dioxide in very low concentrations are disinfectants. Then anti-fertility drugs. Antibiotic revolution has provided long and healthy life to people. Life expectancy has doubled. Increased population has caused many social problems, the food resources, environmental issues, employment issues, etc. Control these population is required to control, and it has led to family planning. Anti-fertility drugs are of use in this direction. Birth control pills, they contain a mixture of estrogen and progesterone, and both of these. That is, what do they do? They suppress ovulation. Synthetic progesterone derivatives are more potent than progesterone. So synthetic progesterone derivatives, they are more potent than progesterone. Norethindrone. Norethindrone is an example of synthetic progesterone derivative most widely used as an anti-fertility drug. So basically, if ovulation won't happen, then the fusion won't happen. Fusion won't happen, then zygote will not be formed, then embryo will not be formed, implantation won't take place. So basically, birth control pills, estrogen, progesterone से your initial process ovulation only ये हो जाता है. Now, norethindrone is an example of synthetic progesterone derivative which is most widely used as anti-fertility drug. Estrogen derivative, which is used in combination with progesterone derivative, is ethinyl estradiol or novestrol. Norethindrone and ethinyl estradiol or novestrol. This is a synthetic progesterone derivative, and this is estrogen progesterone derivative combination anti-fertility drug. With reference to which classification has the statement ranitidine is an antacid been given? Is their work as antacids. Therapeutic action. On the basis of therapeutic action. Chemicals in food. So chemicals are added to food for preservation, such as in your jam, pickles, sauces, enhancing their appeal, adding nutritive, enhancing their appeal, your food colors, smell, that is your olfactory, essence. Enhancing their appeal is essence, food color, adding nutritive value to them. Main category of food additives are as follows. Firstly, food colors, then flavors and sweeteners, then fat emulsifiers and stabilizing agents, then flour improvers, anti-staling agent and bleaches, antioxidants, preservatives, nutritional supplements such as minerals, vitamins, and amino acids. Except for chemicals of category 7, that is minerals, vitamins, and amino acid, none of the above additives have nutritive value. So except for this is the only one which has nutritive value. Rest, none of them have nutritive value. These are added either to increase the shelf life of the stored food or for some cosmetic purposes. In this section, we will discuss only sweeteners and food preservatives, not other things. So artificial sweetening agents. What are the natural sweeteners? The natural sweeteners are sucrose, add to calorie intake, and therefore many people prefer to use artificial sweeteners. Sucrose add to calorie intake, and therefore so basically natural sweetener is sucrose, but due to sucrose, that is calorie increases, and hence people prefer artificial sweeteners. Orthosulfobenzamide is called saccharum. It was the first popular artificial sweetening agent. It has been used as sweetening agent ever since it was discovered in 1979. It is about 550 times as sweet as cane sugar. It is excreted from the body in urine unchanged, so not absorbed. It appears to be entirely inert and harmless when taken, and therefore this orthosulfobenzamide, also called as saccharin, it is used extensively or great value for people who have diabetes and people who need to control the intake of calories. And some other commonly marketed artificial sweeteners are aspartame, saccharin, sucralose. Why is this lagging? This is lagging, okay. So aspartic acid part, phenylalanine or methyl ester part. So it has aspartic. Aspartic acid part and phenylalanine or methyl ester part. Then comes your saccharin, which is 550 times more sweet than cane sugar. Then comes your sucralose, which is 600 times more sweet than your cane sugar. And alitame, which is 2000 times more sweet than cane sugar. Wow. ना भी ज़्यादा मीठा नहीं पसंद। Aspartame. Aspartame is the most successful and widely used artificial sweetener. My stylus stopped working. Stylus stopped working. Okay, aspartame is the most successful and widely used artificial sweetener. It is roughly 100 times as sweet as cane sugar. Methyl ester of dipeptide formed from aspartic acid and phenylalanine. Use of aspartame is limited to cold food and soft drink. Why? Because it is unstable at cooking temperature. This is very important. Allictame is a high potency sweetener. Although it is more stable than aspartame, control of sweetness is difficult while using it. Sucralose is trichloro derivative of sucrose. Its appearance and because it is 2000, this is 2000 times more. So even if you put a little bit, it becomes too sweet. Its appearance and taste are like sugar. It is stable at cooking temperature. Does not provide calories. Sucralose is basically the most efficient or well preferred. Now, food preservatives, they prevent spoilage of food due to prohibiting microbial growth. Most commonly used food preservatives include table salt, sugar, vegetable oil, sodium benzoate, C6H5CONA. Then sodium benzoate is used in limited quantities and is metabolized in the body. Salts such as sorbic acid and propionic acid are also used as preservatives. Why do we require artificial sweetening agent? Because your natural uh, sweetening agents such as sucrose, firstly it increases your calories, secondly it can increase your blood sugar level when it comes to diabetes person. So therefore if we eat artificial sweeteners, and artificial sweeteners as it is, they pass in our urine, that is without getting absorbed by our body, so therefore they are harmless, and plus they will not increase our calories also. So therefore we that is artificial sweeteners are preferred. Antioxidants in food. Antioxidants are important and necessary food additives. They help in food preservation. They retard the growth of action of oxygen on food. Okay, what are the artificial sweeteners? Aspartame, allictame, and sucralose. And before that, saccharin. Sucralose, saccharin, aspartame, and allictame. Okay, food preservatives. Then antioxidants, important necessary food additives, help in food preservation by retarding the action of oxygen on food. How do antioxidants in food, they help in preservation? That is, they retard the action of oxygen. They act through several chemical mechanisms. Two of the most familiar antioxidants are butylated hydroxytoluene (BHT) and butylated hydroxyanisole (BHA). Addition of butylated hydroxyanisole to butter increases its shelf life from months to years. Sometimes butylated hydroxytoluene and butylated hydroxyanisole along with citric acid are added to produce more effect. Sulfur dioxide and sulfite are useful antioxidants for wine and beer, sugar syrup, and cut, peeled, or dried fruits and vegetables. Some BHT and BHA along with citric acid, they are added to produce more effect. Sulfur dioxide and sulfite are useful antioxidants for wine and beer, sugar syrup, and cut, peeled, or dried fruits and vegetables. Cleansing agent, you will learn about detergent. Two types of detergent are used, soaps and synthetic detergent. They improve the cleansing property of water, help in removal of fats which bind to other materials to the fabric or the skin. Glycerol ester of stearic acid is fat plus sodium hydroxide gives us sodium stearate and glycerol or glycerin, which is used as soap bar. Soaps are the detergents used since long. Soaps used for cleaning purpose are sodium or potassium salt of long chain fatty acid, example stearic, oleic and palmitic acid. Soaps containing sodium salts are formed by heating fat, glycerol ester of fatty acid with aqueous sodium hydroxide solution. This is known as saponification. In this reaction, esters of fatty acid are hydrolyzed and the soap obtained remains in colloidal form. It is precipitated from the solution by adding sodium chloride. Let's do this in the next last part, 2 pages.